x, and notice that it goes to 0 very, very fast with x. E to the minus x squared. It's a Gaussian. It's a bell-shaped curve that goes to 0 as e to the minus 1/2 omega x squared, and is very, very square integrable. If we square it and integrate it, it's extremely convergent. And so we've succeeded in finding, now we can go back and check that the original Schrodinger equation is satisfied. In other words, we could plug this wave function into the Schrodinger Hamiltonian up above and calculate what the energy eigenvalue is. Well, we already know what it is. It's going to be omega times 1/2. We know that from all the algebraic tricks over here. So if we stuck this function back into the Schrodinger, into this Schrodinger equation, we would discover that E is equal to 1/2. Just by putting it in, plugging it in, and doing it. So we know the ground state wave function. We have one eigenvector of the energy. We see what its physical properties are. It's concentrated near the origin. It's very smooth because the Gaussian function is very smooth. It's concentrated near the origin. It does what you might expect a ground state wave function of a harmonic oscillator to do. It just sits at the origin. Sits very close to the origin, or at least by close now I mean that it's concentrated near the origin. And, yeah, it's the ground state. What about the first excited state? I'll do the first excited state for you. It's almost trivial, and then you can go home and have a lot of fun calculating the next 50 states. It's sort of mindless fun, but how do you do it? It's how you do it that's more interesting than what you get. Well, oh, they're both interesting. But you do it by saying, look, I know what the first excited state is abstractly. Abstractly, the first excited state is equal to A plus times the ground state. I know what the ground state is, and I know what A plus is. So let's just apply A plus to the ground state. Here's the ground state. A plus is P plus I omega X, and that will tell us what the first excited state is. All right, so in terms of wave functions, psi 1 of X is equal or proportional to P plus I omega X. Now P is minus I d by dx plus I omega X on e to the minus 1/2 omega X squared. So all we have to do now is to calculate a derivative. But you know, I already did this. We did it with the opposite sign here. We did it with A minus to get 0. If I do it with the opposite sign and get 0, that means if I do it with the sign here, I'm just going to get twice the answer that I would get. Go back. I did this operation on here and got 0. That's the way I solved the equation. All right, so if this plus this acting on this gives 0, then it must mean that this term and this term give the same thing apart from the sign. Well, once I know that, then I know that when you change the sign of the over here, instead of having them cancel, they'll just double the answer. So this is just going to be twice I omega. That's not so interesting. It's just a numerical factor. Happens to be imaginary, but who cares? But it has X times e to the minus 1/2 omega x squared. So structurally it's different. It's not just the Gaussian function, it's the Gaussian function times x. What does that look like? That looks like this. Again, it's very small, far away. The fact that there's an x here doesn't make it big far away because it's totally overwhelmed by the e to the minus x squared.
So it has to be minus. It has to be minus when x is negative.
Yeah, good. It's negative, yeah. Well, it's twice an imaginary number times omega. Right. But whatever it does on one side, it has the opposite sign on the other side. It's an odd function. Odd meaning it changes sign when it goes through the origin. Right. So let's make it negative on this side. Goes down, and then comes up 0, and then goes to 0 again. It's odd, meaning to say that when you reflect it, it changes sign. It's anti-symmetric. You would say it's anti-symmetric. The probability, which is the square of this, is symmetric. But notice that the probability goes to 0 at the origin. If you're in the first excited state of the harmonic oscillator, the probability that you find the oscillator at the origin is 0. Interesting fact. That's the first excited state. It has the ground state had no nodes. A node means that the wave function is 0 somewheres. The ground state had no nodes. The first excited state has one node. Each time you act with A+, you can just spend a little bit of time with it. You'll see how it works. Each time you act with A+, you make a higher order polynomial in front of e to the minus omega. Each time you hit it with another A+, it'll give you x squared plus another term.